Today I am going to focus how to solve the numericals of the modern physics, and especially the chapter is motion of electron in electric field. So first your topic, motion of electron in electric field. There are different situations. So first, number one, when charge remains stationary in electric field. If any charge, any drop of liquid remains stationary in the electric field, and electric field is applied across the parallel plates, if the electric field E, potential difference B, and separation between the parallel plate small d. So E is equal to V by D. Electric field equal to potential difference by separation or distance between the parallel plates. If any charge remains stationary in electric field, and if the charge or electrons remains stationary, it means the upward force is equal to the downward force. Upward force, the electrostatic force, equal to downward force means weight of the well drop, weight of the charge, weight of the electron, and whatever. So Fe is equal to Fm. Fe means QE equal to mg. So this is the equation number 1. First, and E equal to V by D. So sometimes QE equal to QV by D equal to m. So density into volume. So volume 4 by 3 pi RQ. Volume into density into G. So the above equation is also written as QE equal to QB by D 4 by 3 pi RQ rho G. This one is the 1, this one is the 2. E equal to electric field, where E equal to electric field, V equal to potential difference maintained, established across the parallel plate capacitor, D equal to separation or distance, Q equal to charge, rho equal to density of liquid or oil, G equal to acceleration due to gravity. So this is the condition when charge remains stationary, means downward force due to weight is equal to upward force, electrostatic force. Now second, in the similar condition, when the charge is moving in upward direction with terminal velocity v. So at that moment QE equal to 4 by 3 pi RQ rho G, this term, and plus 6 pi eta RB. This is the coefficient of viscosity, radius of the drop of liquid, and V is the terminal velocity. So this formula can be used when the charge is moving in upward direction with the terminal velocity V, where eta, coefficient of viscosity, radius of well drop V equal to terminal velocity rho equal to density of liquid or oil, E equal to electric field. So this is the second type of question when now when charge is moving in upward direction in viscous medium, and if the charge remains stationary in viscous medium, so there must be adding the part this one QE equal to 4 by 3 pi RQ rho minus sigma G, where rho equal to density of medium. And similarly here, if there is the density of medium in this space, so QE equal to 4 by 3 pi RQ rho minus sigma G plus 6 pi eta RB. Rho is the density of oil drop, this one, and sigma with the density of medium. So there are the two different types of the formula in the same type of the question. When charge remains stationary, if there is no medium at that moment, Q is equal to this much, and if there is the density of medium or the medium presence having the density rho, so QE, and both equation for charge remains stationary, charge is at rest between the electric field. Charge is in motion if there is no any medium at that moment, if the medium presence and moving, and the charge moving in upward direction at that moment, this equation or equation like that. So QE equal to 4 by 3 pi RQ rho minus sigma G plus 6 pi eta RB. So this is the second type. And now third in electric field. This is the electric field. Charge enters with velocity v and finally emerges from the electric field from the parallel plate. Sorry. Plus this is not anything. This is the parallel plate, plus plate and minus plate. Charge enters with velocity v in the electric field E. So there is the deflection produced Y. So deflection in electric field experienced by the charge. So Y equal to half AT square. AT means F equal to MA. F is equal to QE by MA. So half QE by M, and velocity is equal to distance by time, where L equal to length of the plate and D is the separation between the plate. So QE by M and T is equal to L by V square. So this is the deflection produced by the charge in electric field. or this is also written as half E by M, capital E, L by V square. It is noted that E is equal to V by D. Capital V potential difference and a small v is the velocity. So always remember this thing. A small v distance by time, capital E potential difference by separation. And finally, what is the angle when the electron, when the charge emerges from the electric field at that moment? Tan theta equal to Vy, and this one is the Vx. So Vy by Vx, Vy means 80, Vy means 80, or A means E by M, V A T, and T is equal to L by V and V, L by V and V, V square, V square. So tan theta equal to EEL by MV square. This is the angle. And last, what is the final velocity when the electron emerges, when the charge emerges? So at that moment, V dash equal to Vx square, Vy square. And horizontal component always remains constant. So this is the V square. And Vy means this term, EEL by MV. L by MV square. So this is the 1, 2, 3, 4, 5. This one is the 6, 7, 8, and this one is the 9. These all are in regard of the motion of electron. Either is in motion, horizontal motion, vertical motion, charge is at rest. So to solve the problem, first find out what is the situation, what is the condition, what is the status of the charge. So first, if the charge remains stationary between the parallel plates, so this one, charge is in motion and moving in upward direction, so this one, or this, if the medium is present. If charge enters like that and shows the vertical deflection in the electric field, at that moment vertical deflection y is equal to this much. What is the angle of emergence, tan theta, and what is the velocity, final velocity when the electron, when the charge coming out from the electric field. And now come to the second. This is the motion of electron or charge. It may be proton. Motion of electron or charge in magnetic field. So if this is the indication of the magnetic field, cross magnetic field, and strength capital B. It means the magnetic field acts perpendicular and directed inward. So this representation is known as the cross magnetic field, and if it is represented by the dot magnetic field, dot magnetic field is represented by capital B. Dot magnetic field acting perpendicular to the plane of paper and directed outward. So if the charge enters with the velocity v, so force experienced by the charge in magnetic field BQV, and if the charge placed in the magnetic field perpendicular to the direction of magnetic field. So this is the velocity and charge acts like the perpendicular at that moment. So the charge or electron revolving in the circular path. So at that moment force is equal to mv square by r. So if the motion of electron, motion of charge enters the magnetic field, where the magnetic field acts perpendicular either in cross magnetic field or dot magnetic field, only there is the change in the direction like this, or it may be, which depends on the nature of the charge q. So force is equal to bqb, force is equal to mv square by r, and mv square by r equal to bqb. So to find out the radius, r equal to mv by bq, and if there is no motion is given, a small v, so the v can be calculated by this equation. ev is equal to half mv square. Energy gained by the electron when it is accelerated by the potential difference v, this is equal to the kinetic energy. So v is capital V equal to potential difference, and a small v is equal to velocity of electron, velocity of charge. This is the first condition. And one of the condition, if electric field in the downward direction like that, and magnetic field also applied perpendicular to it in this situation, means the path remains undeflected. If the both electric field and magnetic field applied perpendicular to each other to the path of the charge, so the path of the charge remains undeflected. So if path remains undeflected, so it is possible only when electrostatic force is equal to magnetic force, QE equal to BQV, or EE equal to BEV, V equal to E by B, and also this equation can be used, EV equal to half mv square. So if the path remains undeflected in both electric and magnetic field, if the charge is in circular path, and if the charge is in circular path when the charge enters perpendicular to the direction of magnetic field, so at that moment, so there is mainly two equations. First, electrostatic force first magnetic force equal to centripetal, BEV equal to mv square by r, or r equal to mv by BE. And second, when the path remains undeflected, for undeflected path, electrostatic is equal to magnetic, EE equal to BEV, V is equal to E by B, and in both equation, this equation can be used frequently, half mv square. It is always noted that capital V potential difference, a small v velocity of, that's okay. So before start the exercise, first watch the video carefully and then solve it. Thank you very much.